All right, now let's move on to the last page. So here we'll do question 3A. So 3A, it says to find an augmented matrix of the corresponding linear system described. So we have volunteers X, Y, and Z offered to stuff 864 envelopes for a newsletter with their newsletters for a charity. Volunteer X could assemble 170 per hour, Y 121 per hour, Z 146 per hour. Total time 6 hours. The sum of the number of hours that volunteer Y and Z spends is twice that of volunteer X. So what is the augmented matrix that can be used to find how many hours each person worked? Well, let's first think about what the variables are. So X can represent the hours worked by volunteer X. Okay. Y in that case would be hours worked by Y. Z would be the hours worked by Z. Okay. So we're told they worked a total of 6 hours. That means if we add up all these hours, we get 6. We're also told how many envelopes per hour they can assemble. So that would mean 170 times the number of hours worked by X would be equal to the total number of envelopes. And then we have 121 per hour times Y hours. And then a 146 times Z hours. This would be equal to the total number of envelopes, which was 864. And then finally, this one is this sentence right here. Oops. So if we look here, it says the sum of the hours worked by volunteer Y and Z spent was twice that of X. So what this tells us is Y plus Z was twice that of volunteer X. The total of their hours worked will be double of how many hours X worked. That's not. Yeah. So now all you have to do is just arrange this so that it's in the XYZ format. So just move 2x over and would end up with this. So our 3 equations is this one, and this one. So we can make an augmented matrix. We get 1, 1, 1, 6 from the first equation. 170, 121, 146, and 864 from the second equation. And then the last equation gives us -2, 1, 1, 0. So this would be the augmented matrix we would need in order to solve this problem. Okay. Now let's look at number 4. Let's first clean this up. Okay. So in number 4, we're given 3 matrices and we want to use those matrices to find their solutions. Well, in A, we have all zeros in both corners and ones along the diagonal. So A is an example of a consistent system that has already gone through the Gauss-Jordan elimination process. So this last column is all the solutions set. So assuming we have a solution set X, Y, and Z, This means their solution set would be 4, 3, and -3. Next, let's look at B. All right, so look at the last row of B. It's all zeros, and then you have this final zero. So that just means zero equals 0. So we can actually reduce B into just the first two rows because this is a dependent system. Since it's a dependent system, we could get rid of the last row since that one's all zeros. And what are the equations we get from here? The first equation would be x plus 9y plus z equals 2. And the second equation is y plus 5z equals 3. So the idea here is we want to write x and y in relation to z. So from this equation, let's move z over and we get 3 minus 5z for y. Now we're going to use that and plug it into the first equation. So we get x plus 9, 3 minus 5z plus z equals 2. So we get x plus 18, no, sorry, 27 minus 45 plus z equals 2. Okay, and then that would just reduce to 44z. Okay, now let's move everything over to isolate x. So it'll be 2 minus 27 plus 44z. All right, so now if I write the solution set to this, because it's a dependent system, you would write -25 plus 44z in the place of x, then 3 minus 5z in the place of y, and then z in the place of z. So this means that for any value of z, we could generate all these values for x and y to create infinite solutions. Okay, and then finally, let's look at a third matrix. So the third matrix, we have C. If we just look at that last column, this is 0, 0, 0, and then a number here. Well, what that means is that we have a contradiction because this is essentially saying 0 equals a number. Well, that's a contradiction. Hence, C has no solution. All right. Okay, and then finally, in question 5, it gives us 3 matrices and it wants us to use back substitution to find the system, the system of equations. So I'm just going to go ahead and solve it for C, since the procedure is the same for all of them. Okay, so C tells us what we could do is convert these matrices back into equations. So we get x plus 2y times 0z, so there's no z in this case, equals 2. The second equation would be y plus z equals 10, and the third equation is z equals 5. So back substitution, since we already have z equals 5, we could plug that in to the second equation, y plus 5 equals 10. So y is equal to 5. And now we're going to put both z and y into the first equation. Now the z is zeroed out in the first equation, so we just have to plug in the y. X plus 2 times 5 equals 2. So x plus 10 equals 2. So x equals 2 minus 10, which is -8. So our solution set would be -8, 5, 5. And that's how you can get the solution set using back substitution when the matrix is in this Gaussian form or row echelon form. Okay, and then that's the end of the review.